Okay, let's get started. Bonsoir à tous. Welcome everybody. Thank you so much for coming on to this jug session in August. This is the first for us. C'est la première fois qu'on organise une session du jug pendant l'été, donc c'est un peu une nouveauté pour nous. Mais c'était l'opportunité d'accueillir Simon. It was actually the right opportunity to welcome Simon, who is actually traveling nearby during those days. So before we give you the microphone, Simon, just wanted to introduce ourselves. For those of you who come here for the first time, si c'est pour la première fois que vous venez, nous présentons à vous. Donc moi c'est Anthony, je suis le président du JUG. Il y a Romain qui est secrétaire, Ludovic trésorier. Ensuite on a Félix, Marion qui ne sont pas là ce soir, je pense. Miali, il est peut-être en train d'ouvrir la porte. C'est celui qui vous a ouvert la porte. Merci beaucoup à lui, le pauvre. And before getting into more details about us, we would like to welcome on stage our host for tonight, which is Madeleine from TS Imagine. Madeleine, si tu peux venir ici nous parler de vous, if you can actually talk to us about who you are.
Hi everyone, I'm Madeleine. I'm the HR and Office Manager of TS Imagine. I don't know if you're familiar with TS Imagine, but I can give you just a brief description regarding our growth. So I guess everyone knows Henry Tremblay. Henry was the first person hired in Montreal office, and this happened in 2019, and he's also a Java champion, as you know. At that moment, the company was under the name of Trading Screen Canada, and in 2021 there was the migration the fusion between two companies, and Imagine Software and Trading Screen, and this is how the TS Imagine is born. I joined the company after the merger, so at that time we were only 15, and we had a really important growth over the last 5 years, so we are now 102 people. As you can see, we have different departments created. We have a development team, QA, we have also support team, data team, and now we are trying to focus more on the AI. So we have also our head of artificial intelligence in Montreal. She was initially transferred from Hong Kong. And we also have a marketing team, and I have my colleague Eloise. She will be with you until the end of the evening, and she's our marketing coordinator. Regarding the recruitment, at the moment we have a few roles, so you can check our website at TS Imagine Careers or our LinkedIn page, and if you are interested or if you know someone who knows, for example, Python, SQL, Snowflake, because you are looking to hire lead Snowflake developer, and also business intelligence developers. We don't have a Java developer role at the moment, but it might change starting September. So that's all. I don't want to take too much time. I wish you everyone a nice evening, and enjoy.
Merci beaucoup. And once again, thank you very much for hosting us tonight, and also for providing food to our audience. That's super appreciated. Thank you very much, TS Imagine. Okay, if you don't know yet, we are using Linktree. We have a Linktree code, so you can scan this QR code, and thanks to that, you will find everything you want to know about us, like the website that we have, the Slack, our YouTube channel, because you know what? Tonight is actually recorded. So you see this little phone right there. So it's recording the sessions for tonight. So in case you cannot come because, I don't know, it's too cold or whatever, then you can follow us online if you want to. We also always try to get new sponsors and also have new hosters, just like, so TS Imagine tonight is hosting us. But believe me, sometimes it's pretty hard to find a place to host a Java user group. So if your employer, by any chance, is happy to see a nice crowd of Java developers, please be in contact with us, please. And also if you have some spare money to have your logo on our slides and everywhere, same thing, you can apply as a sponsor as well. On organise aussi, donc Montréal Jug, on a une association sœur qui s'appelle Devox Orchids, et tous les trimestres, donc c'est moins souvent, c'est tous les trimestres, on organise des ateliers avec des enfants âgés de 5 à 14 ans. C'est le fun, on a plusieurs ateliers spécifiques à leur âge, et ça dure une journée. Et sur une journée, on va voir des enfants et on va les accueillir et leur faire découvrir la robotique et un petit peu l'informatique. Même chose, always the same link. You can feel free to join as a volunteer for Devox Orchids as well. What else do we have? Tac. Also, if you want to present a topic, si vous voulez présenter un sujet, n'hésitez pas à nous rejoindre, la même chose. Et si vous voulez nous aider, rejoindre l'équipe, pareil, vous pouvez nous contacter. You're always free to join us. Okay, so what happened recently? We have, so here this slide is a new slide. So basically those are like what is hot on our Slack channel. So if you're on it, maybe you already noticed, but if you're not, we hope that you will want to not miss any information on our Slack channel. We have Jonathan L'Hermitage, who is based in Lyon, who always gives us some insight about JetBrains because he's a plugin author. He wrote many plugins for IntelliJ, so he's always talking about giving us like the latest news about what's going on with IntelliJ. And apparently there was a campaign that happened against with malicious plugins. So be careful when you install your plugins from IntelliJ because some AI plugins are not what they are supposed to do, are not doing what they're supposed to do, so be careful. Also, I shared a link last month because there is a Java documentary. So this Java documentary, it follows many other documentaries by the same company actually. I think those people, I can't remember their name. What is the name? I can't remember. Anyways, I think they are based in England, I think, or Holland. Anyways, they're a European company. And they have made many documentaries about tech circles such as Kubernetes, Spring, and lately Java. So they did this documentary. You can go to YouTube, just look for Java Story official documentary. I think it's a 1 hour long, and they have some very interesting guests such as the father of Java, Mr. Gosling, and many other people, as you can see here on the picture. So super interesting. They tell you about the history, like the first days of Java. It was not supposed to be what it became, and blah, blah, blah. It's super interesting. So I invite you to have a look at this documentary. It's pretty well done, honestly. Also, what are the next events? C'est quoi les prochains événements? Locally, in Montreal, we have our friends from Dev Montreal. It's going to happen in November 27. So you know, it's their third edition. C'est la troisième édition seulement qu'ils organisent. Avant, ils étaient à l'ETS. Et là, je crois qu'ils se déplacent sur Concordia to have bigger rooms to host you because it's pretty popular. What else do we have? We have a bunch of other conferences that were added right there. There's a website that you can actually bookmark, dev.events/java, that actually gathers all the events related to Java, if you want to. Also, obviously, Montreal Java User Group, we will meet again in September. When, where, about what? We don't know yet. You'll see. Just stay tuned on the social networks and on Slack. Okay, very important. If it's the first time you come here, we have two IntelliJ, two JetBrains license to win. So they are IntelliJ Ultimate licenses. Actually, they are coupons. So the way that we give them away to the people among you who are listening the best. So basically, we're going to run a quiz at the end. So be careful about what Simon is about to say, because we'll ask you a question. And then, if you're fast and if you remember what he said, you shall win a license. Please join our Slack, you know about it. Thank you very much. Merci à tous d'être venus ce soir. Passez une bonne soirée. And it's you now, Simon.
Yes. Right. Good evening. Bonsoir. Unfortunately, that's where the French stops. My wife, who's Canadian, I spoke to her earlier on, and she said, they do know you're not presenting in French, don't they? And it's like, yes, it's definitely going to be in English. Right, so the first session I'm going to do is called Modern Java Puzzlers. The idea behind this is audience participation. Do not be alarmed. It doesn't require a lot of participation. What it requires you to do is to vote. So all you have to do is put your hand up when I ask a particular question. And the idea is to sort of explore some of the newer features in Java and look at some of the ways that they behave in interesting ways. So before we start, I do have to have a disclaimer. I'm going to be very clear about this, because when I put this session together, I was asking some questions on the Amber mailing list, and I was talking to Brian Gertz. And Brian Gertz, I said I was doing this session on Java Puzzlers. He said, oh, I don't really like Java Puzzlers because they make people think that we haven't thought through all of the features that we're adding in terms of the language. And so I have to be very clear that this is not designed to be a critique on the design of language features in Java. I actually have nothing but respect for people like Brian, people like Gavin Bierman, Alex Buckley as well, who's the person who looks after the Java SE specification. He's the one who actually does the Java language specification. His job is not an easy one, as we will see as we go through the presentation. So I think that this is not about trying to catch people out. It's not about saying these language features haven't been thought out. It's just about understanding some of the nuances of how these things work. Now, the other thing we need to understand is, what do we mean by modern Java? Because, of course, Java is now over 30 years old. What are we talking about in terms of modern? We could be saying the last 10 years, we could be saying the last 5 years. But in essence, what we're doing here is we're talking about things that have been introduced over the last few years as part of Project Amber. And that's small changes to the language which are intended to make the language smoother, take off some of the rough edges. And specifically what we're going to be looking at are things around patterns. So there is pattern matching in Java, that's been around for a while. Several different aspects of that have been added. I'm just going to take my watch off, so I can keep an eye on the time. We will talk about switch expressions a lot, because there's a lot of interesting things that happen there. And then we'll also talk about mixing primitive and reference types in both patterns and switch expressions. And that's where life gets really interesting. So the way this works is I'm going to present you with a piece of code on the screen, and you need to have a look at it, and I will ask you a question about how it works, does it work, what does it do, and then you get to vote. Now, the way this works is it starts off really easy. So the first couple, you're just going to go, oh yeah, this is right, I can do this. And then we'll start getting harder. And by the end of the presentation, your brain will be boiling in terms of trying to understand what it is that's going on, and when I try to explain it to you as to how this actually works. Okay, let's start with section 1, which is exhausted by exhaustive. So my first puzzle here is a very simple piece of code. Most of these are very small pieces of code. What I've got here is a switch expression. This is a new feature in Java. We had the switch statement from the beginning of Java, but now we have a switch expression that can return a value. So I get my value as an int, primitive, and then I switch on X, and I've got a case for 0, a case for 2, 4, and 6. So my question to you is, who thinks that this will compile? Nobody. Oh, one person. Who thinks it won't compile? Okay, right, good. So the answer is, it will not compile. Now, the reason it won't compile is because it is not exhaustive. And what the developers said is that in the situation where we're using a switch expression, they want it to be exhaustive, meaning it needs to cover every single possible value that we can pass to that. Now, technically, there's nothing wrong with the way that we've structured this, and they could have designed it to pass that without any problem. But they said that the idea behind this is to try and eliminate as many errors as possible at compile time will make it exhaustive so that you don't miss things that maybe you actually wanted to deal with. So that won't compile. What about if we add a default clause? Who thinks it will compile now? Ah, good. See, I said it was easy. You know, some of these are easy. So yes, it will compile because we have a default clause, which means that anything which is not 0, 2, 4, or 6 will be caught by the default, and that means it is exhaustive. It will catch every value that we can pass to it. So there's no problem with that. Okay, what about if we now use a switch statement? Not a switch expression, a switch statement. So we have our x equals get value. We're now having a string d, which we'll assign to be null, and then we will assign a value to d based on whether it's 0, 2, 4, or 6. Who thinks this will compile? Oh, good, yeah. Who thinks it won't compile? Oh, a couple of people, yeah, okay. Well, yes, it will compile. Absolutely, it will compile because a switch statement does not need to be exhaustive. And there's a very good reason for that, which is that when Java was first developed, a lot of the syntax was lifted directly from C. And the switch statement is an example of that. So they literally took the same syntax that you use in C, make it familiar for developers, and they just understood how it worked. So in a switch statement, because it hasn't been exhaustive in the past, if we tried to make it exhaustive now, it would break a lot of code because lots of people have relied on the fact that it doesn't have to be exhaustive. So rather than breaking lots of code, they said switch expressions need to be exhaustive, switch statements still don't need to be exhaustive. Okay, what about if we do this now? So now we're going to have our string d here, and we'll take an integer. So we're using a wrapper class, meaning that we have a reference type rather than the primitive. We'll switch on x using a switch statement, and then we'll have case 0, case 2, 4, and 6, and case for null, because we may have a null reference. Who thinks this will compile? Ooh, nobody. Who thinks it won't compile? Okay, the answer is that, oh yeah, sorry, that's the integer. Yeah, the answer is it won't compile. But it's a switch statement. So a switch statement doesn't need to be exhaustive. Why do we get the error message, the switch statement does not cover all possible input values? I said the switch expression needs to be exhaustive, a switch statement doesn't need to be exhaustive. This is a switch statement. Why is it complaining? The answer is there's actually 3 types of switch in Java now. There is a switch statement, there is an enhanced switch statement, and a switch expression. This is an enhanced switch statement. What do I mean by that? Well, the fact that we can have a case for null. Prior to the introduction of the switch expression and the changes in syntax that we've had here, you couldn't have a case for null. It didn't make any sense because the switch statement allowed you to switch on integral types, enumerations, and strings. So there wasn't the capability to have a null in that situation, so that wouldn't be possible in the past. So the developers again said, right, we don't want to break backwards compatibility, but nobody could have written this code as it's put here in the past. So we'll call that an enhanced switch statement, and we'll make it exhaustive. So that's the first thing we need to understand, is that this even though it's a statement, does have to be exhaustive because it is, has a null in it. Yeah, so that's basically what I've just said, so it must be exhaustive. Right, what about if we use an enumeration now? So we have an enumeration called AB, and that contains two values, A and B. I have a test AB method, which has a switch expression, and it has a case for A and a case for B. So who thinks that this will compile? Ooh, lots of people think it will compile. Who thinks it won't compile? Nobody. Okay, good. It will compile. Very good. Because it is exhaustive. We have an enumeration which has values A and B. We have a case for A. We have a case for B. Okay, this is all good. What about if we change that to having a switch statement and we have a case A and a case B? They return A or return B. So we've still got the same enumeration, we're just doing a return from the different cases. Interestingly, you have to put braces around that. It won't work with just a return, you have to put braces around it to make it actually work. Who thinks this will compile? And see, people are starting to get a little bit unsure about this, aren't they? It's going to get worse. Who thinks it won't compile? Okay, a couple of people who think it won't compile. Well, the answer is it will not compile. It will not compile, and it says it has a missing return statement. And you go, hang on, why has it got a missing return statement? I've got an enumeration which has A and B in it, and I've got a case A returns A, case B returns B. How can I possibly pass something to that which doesn't return? The answer is that you have to look into the Java language specification. And in there, you will find there is section 13.4.26, which states adding or reordering constants from an enum type will not break compatibility with pre-existing binaries. What that's essentially saying is that if that enumeration was in a separate source file and we compile all our code, that will work fine. But if I then go back and I change my enumeration AB and I add a C to it, I can compile that and generate a new class file which has an enumeration which has 3 values in it. If I pass that to my test AB and I've got a C in there, there is no return statement for C. So there's no return statement from the method. The compiler rejects it because of that. Okay, that is logical. I get that. However, let's return to the previous example, which uses a switch expression. Now, I'm thinking that's exactly the same as the previous one in terms of I could have enumeration AB in a separate source file, and I could add a C to it, and I could recompile it, and then I'm going to have a situation where my switch statement is not exhaustive. So why does the compiler let me get away with that? To solve that, we have to look a little further into the Java language specification, and we find that there is a statement in the same section that covers the previous one, and it says, as with sealed classes, although adding an enum constant to an enum class is considered a binary compatible change, it may cause the execution of an exhaustive switch to fail if the switch encounters the new enum constant that was not known at compile time. So this is one of those sort of odd situations where you think, I'm not quite sure why they did that, because they could have had the compiler rejected because it isn't technically exhaustive if you could change the enumeration, but they didn't do that, even though they do it for the switch statement. So that's one of those things that, you know, a little bit odd in terms of the design decision. I've never managed to get to the bottom of why they did it that way, but be aware that that is the case. Okay, section 2, primitives in patterns. So obviously Java is an object-oriented language. And again, when we look back at the very early history of Java when it was developed, the original goal had been to treat everything as an object, and that would have been good. But if they did that with the performance of the machines we had in 1995, for those of you old enough to remember what PCs were like in 1995, it wasn't very good. So the only way that they could get the performance of Java to work the way they wanted it to was to include primitives so that they didn't have to have object references for numbers and characters, for example. So that meant that we have both primitive types and reference types. And then there's a sort of overlap, because we obviously have our wrapper classes, where we've got an int as a primitive, we have an integer wrapper class, and then float, and so on. The other thing that they introduced in JavaSC 5 was auto-boxing and unboxing, which means that where we have primitives being used and we need an object reference, rather than having for us as developers to explicitly create an object with the value and then on the way back extract the value, the compiler will do that for us. It will box a primitive value into an object reference where needed, and it will unbox it where we need a primitive value. Now, you could argue that auto-boxing and unboxing is not actually that good a feature, and I'm going to show you some examples why I think that. The other thing is that since JDK 23, we now have the ability to include primitives in patterns as a preview feature. Now, this is very important. It's still a preview feature in JDK 26, and in fact, JDK 27, it's also a preview feature. There's a very good reason for it still being a preview feature, again, which I will show you in a moment. How and when exhaustiveness is required can sometimes require quite a lot of thought. And there's also what we call pattern dominance. When we deal with switches, we have pattern dominance, and I'll explain that more as we go through. These are things we need to consider. So, primitives in switch. So what I've got here is, again, my test int. I'm passing in an int. And then I'm using a switch expression, and I've got switch on n, which returns a string r. I've got a case for byte, and I've got a case for int. B returns byte, I returns integer, and then I print out what it is. And yes, I am still using system.out. I know I could use io.println, but I'm old school. So my question is, will this compile? Yes, it will compile. No, it won't compile. Yes, now we're starting to get that. I don't know the answer, I'm not going to vote. So the answer is, yes, it will, because the switch is most definitely exhaustive. So it's a switch expression, needs to be exhaustive. We are passing an int as a parameter to the method. We are switching on an int. Because we have a case for int, any value that I can pass to that will be caught by the case for int. Therefore, it is by definition exhaustive. So we don't have to worry about that in this situation. Right, what about if we add a default? So we have case byte, case int, and a default. Who thinks this will compile? Okay, who thinks it won't compile? Okay, a few people. It won't compile, no. And the reason it won't compile is because it says the switch has both an unconditional pattern and a default label. Again, the fact that we're passing an int in and we have a case for int, everything that we can pass into that method will match against the case int. That means the default will never be used, it's unreachable, and so the compiler says, yeah, there's no point in having a default there, you need to rethink your code because it doesn't make any sense. Question?
For case byte B,
yes.
Is that not unreachable?
Why would it be unreachable?
Well, you're passing in an int, so there's the pattern.
Yep.
A byte is
8 bits.
8 bits instead of 16, so you're never going to match that.
Aha. Hold that thought for one moment. Because let's have a look and see what happens if we pass a value to it. So we know it compiles. So now let's think about what happens when we pass a value in. So if I call testint with 1024, who thinks it will print byte? Okay, interesting choice. And who thinks it will print integer? Okay, yes. So it will print integer. Now this is important because what's happening here is we pass in the value of int. And because we have a primitive, which is one that can be expressed in different forms depending on the width of the number. So an int is 32 bits, a short is 16 bits, and a byte is 8 bits. So all of them represent integral values, but there are different sized integral values. In order for this to make any sense, in terms of is byte reachable, we have to have a runtime check. So now this is moving away from a compile time check to a runtime check. The compiler will insert code that says, if we pass a value into test int, even though it's an int, we'll look at how big that number is, and we'll add code to say, does this number fit into a byte? If it does, it will match that case. If it doesn't, it matches against the case for int. So here we have 1024, it won't fit into a byte, so we match on int. What happens if we do test int 42? Who thinks we will get byte? Who thinks we will get integer? Okay, we get byte, because again, although we're passing an int value in, 32-bit wide value, the value stored in there is 42. 42 will fit into a byte, and so we match against the case. In terms of the pattern is for byte as the primitive value. If we didn't do that, if we didn't have a runtime check, it would basically make the whole idea of having primitive patterns in a switch irrelevant, because it would always, as you say, match against int, because it isn't, we're passing in an int. So there has to be a runtime check involved. What about if we cast the 42 as an int? So we're saying, we really mean this as an int. So who thinks we'll get byte? Okay, who thinks we'll get integer? Okay, and the answer is we get byte. Because even though we cast 42 as an int, we're passing it as an int. So what's arriving is an int. We then do the runtime check. We're still doing the runtime check to see, does 42 fit into a byte? Yes, it does, and so it's fine. So there is no problem with that at all. What about if we do test int integer dot value of 42? So now we're creating an integer reference type, a wrapper class, object reference, and then we call our method and we say, does it give byte? Does it give integer? Okay. The answer is it gives byte. Now what's happening here is, yes, we are creating an integer object, but the problem is that the method signature requires us to pass in a primitive int. What happens there is that the compiler will do auto unboxing. It will simply say, oh, you've created a reference type. It's not a primitive, so we'll just unbox that for you, create an int, pass that as a parameter, do the runtime check. Does 42 fit into a byte? Yes, it does, so it matches byte. Oh yes, what about if we switch the order? What about if we say case int first and then case byte second? If I do the same thing and pass in integer.value of 42, now who thinks, do we get integer? Who thinks we get byte? Okay, the answer is it won't compile. It won't compile because we've got pattern dominance. And pattern dominance is all about that unreachable code. So we saw an example where we had the default after the int pattern, and we couldn't reach default because everything that would be passed in could match against int. So the same thing applies here. If we have case int, that will match everything that we can pass in. And it will match 42, it will match 1024, doesn't matter. So that would match everything that we pass in first. So case byte is unreachable. The compiler looks at that and says, because it's unreachable, that's pattern dominance, so we can't compile that code. We get an error message. Just a brief sort of aside, what about primitives with instance of? Because we've talked about primitives with switch. What about primitives with instance of? So if I have int x equals 42, and I say if x instance of int, print out int, who thinks it will print out int? Yes, it will, because 42 fits into an int, And we've actually passed it an int. So it's an int, it fits into an int, no problem at all. If X instance of byte, print out byte. Who thinks it prints out byte? Okay, yes it does, because 42 fits in a byte. And again, we have that runtime check when we're dealing with primitives, because we need to establish which of the sized types it actually fits into. If we do if X instance of byte, print out byte, else if X instance of int, print out int, who thinks we get byte? Who thinks we get int? Good. We do get byte, because 42 still fits into a byte, so obviously matches against that with a runtime check, and everything works. However, if I reverse this, if X instance of int, print out int, else if X instance of byte, print out byte, who thinks we get byte? Who thinks we get int? Very good, yes, because in this case, it's the first match, not the best match. Unlike with a switch, we don't have to worry about pattern dominance. We've been quite explicit here. We're looking for an instance of int, and we've also said otherwise an instance of byte. The compiler won't complain about that. It says if that's what you want to do, that's what it'll do. Don't have to worry about pattern dominance. Okay, back to switch again. So now we'll mix reference types and primitives to make life interesting. So we will have case byte lowercase b, so a primitive reference, and we'll have case integer as a reference type wrapper class of integer. And then because we're passing in an object, because we have to have that if we want to do a pattern for the integer reference type, we'll also need a default in order to make our code compile. So now we need to make sure it's exhaustive, because we could obviously pass in lots of things which are not an integer, and that would they'll be caught by default. So if I do test obj integer dot value of 42, who thinks it will print out integer? Okay, a lot of unsure people. Anybody think it'll print out byte? Ah, okay, right. So the answer is it prints out integer. Why does it print out integer? Well, what we're doing here is we're passing in an integer object that we have created. So we have a reference type of integer, we pass that in, and then we do a switch on that. Now, what's happening is that the compiler is saying, well, you've passed me an integer object, and you've got a pattern for integer class. That matches. So that is a match. But the important thing about this is if you read the JEP, that is what's called unconditionally exact, meaning that the type is the same. So it's an integer, it matches against integer, there is no question about that. What about if we do test obj 42? Who thinks we get byte? Who thinks we get integer? Okay, we get integer. Right, so the reason we get integer, first thing is that by doing test obj 42, 42 is something that will fit into a byte. But when we pass it as just a number like that, Java uses automatic promotion. Java will say 42, yes, it will fit into a byte, but when you don't tell it what the size of the primitive is, it will say if it fits into an int, it will treat it as an int. If it doesn't fit into an int, it makes it a long. So it's either an int or a long. There is no situation where you're using 42 like that it will automatically put it into a byte. So what's happening is it's saying, okay, you have an int primitive of 42. We need an object reference. So the compiler will auto box your 42 in an int into an integer object, pass that in, it matches against the integer pattern, so we get integer. Question?
Is there ever a situation where it would auto box to a byte?
Hold that thought. What about if we do this? What about if we make our 42 explicitly a byte primitive? So we're saying create a byte reference and give it 42, and then call test obj on B, And what do we think we'll get here? Will we get byte or will we get integer? Okay, we get byte. Now, the reason we get byte is because we have told the compiler that we want to use a byte primitive. When we call test_obj with a byte primitive, the compiler will auto box it into a reference type because we need an object. Because we've made it explicitly a byte, the auto boxing will box it into a byte wrapper class reference object. That gets passed in, doesn't match against integer because a byte is not an integer. So at that point, the compiler will say, hang on, we've got a byte primitive case, but we've got a byte reference object. We'll unbox it and get a byte from that. And because the value of 42 will fit into a byte, we then match against that and we get byte as the answer. So it's where it starts getting complicated because you've got auto boxing, unboxing happening, and you've got reference types versus primitives. This is where I start to, yes, question.
Yeah, so in this case, the exact type matching is more important than the order of the
Yes.
case.
Yes, exactly. Yes, because we have a reference type, the matching of the type is more important than matching of the value. Yes. This is where I start to tell people, don't do this in your code.
But what we pass, like change the byte to the wrapper class, the byte B.
So if you did that, then you would still match against, so if we made byte a capital B byte, then we would still match that because passing in a byte as a primitive, it auto boxes into a byte, and then you get unconditionally exact pattern matching because you're passing a byte and you've got a byte as a type in your pattern.
And what if we pass 42 like before, like just a regular int?
So then it will match against integer because the automatic promotion will then, yes, same thing, yeah. What have I done here? Hang on. Oh, yes. So what about if we reverse the order of integer and byte and we call test_obj on 42? So first of all, who thinks this will compile? Okay. Assuming it compiled, who thinks we would get integer as the result? And who thinks we would get byte? Okay, so the answer is yes, we do get integer. Now, even though I've reversed the order, there isn't a problem of pattern dominance because we have the reference type there. So in this case, automatic promotion, we get int, we then auto box it into integer and that matches. So then you think, okay, well, how do we get to byte? Well, obviously, if we do this and we say byte b equals 42, we've got a byte as a primitive, call the method with that, auto boxing turns it into a byte reference object. That then gets unboxed, matches against the byte, so byte is reachable. There is no pattern dominance involved when you've got a reference type and a primitive, and you're using reference types as the parameter. Yeah, so that gives you byte. Okay. What about if we do this? So we have case integer as a primitive, as a reference type. Then we have case byte as a primitive, case int as a primitive, and we'll print out integer or int. Who thinks this will compile? Anybody think it won't compile? Yes. So the answer is it won't compile because clearly we have a situation where we've already got integer, we're passing in an object reference, so there's nothing that we could pass in that will unbox and give us an int, which isn't already an integer. So that then means that the case for int is unreachable, so we have pattern dominance, and the so what I've given you there, the first one is what Java-C will tell you is the error message. This case label is dominated by a preceding case label, which makes sense. But I do find IntelliJ, which I know that there's a couple of free licenses going this evening, IntelliJ is very good because they actually give you more meaningful error messages. So it actually says duplicate unconditional pattern for that particular situation. Right, yes, so this one. So we've got case integer, case short, and case byte. So similar to what we had before, so we've got a reference type, then we've got a short, and then we've got a byte. So who thinks that this would compile? Yep, who thinks it won't compile? Okay. Anybody want to try and explain to me why it won't compile? Or are we just kind of guessing?
Because the integer will cover all the things which are covered by the short.
No, because remember, see, the way I look at this, I say to myself, well, if I passed in a parameter and I made it explicitly a short primitive, that would, or even if I create a short object, pass that in, that will get unboxed in the same way a byte would get unboxed to a short, and the short will match against that, and so it should compile. The answer is it won't compile. It says this case label is dominated by a preceding case label. I firmly believe this is a bug, and I am justified in that because I sent this to the Amber mailing list, and I didn't get a reply straight away. And I was at the JCP Executive Committee meeting last November, I think it was, and one of the people who was also there was Gavin Bierman. Gavin Bierman works for Oracle. He's the engineer responsible for pattern matching, primitives, and so on. And I cornered him. I said, look, I've got this thing I'm using in my examples. And I said, it doesn't work. And he said, oh, yes, we saw your message on the Amber mailing list. We've been talking about this for the last week. And he says, yes, it is a bug. So this is one of those situations where there are many kind of competing things that they need to figure out in terms of how to get this to work. Because obviously, like I said, if you passed in a short reference type, it gets unboxed and it should match against short. And that doesn't get dominated. You could do the same thing with byte. So byte is reachable, short is reachable. What about if we do this? So now we're getting our int again from value. So we're doing a primitive, and now we're going to say switch on n, and we'll have case for integer, the reference type, and a case for byte. So who thinks this will compile? Okay. Who thinks it won't compile? Ah, yes. Well, I think it shouldn't compile. And the reason I think it shouldn't compile is because we're using primitives, and the compiler is going to, if I pass anything which is bigger than a byte, it's going to get auto unboxed and we're going to see an integer. But even if I pass in, because I'm matching against integer, it should unbox in order to test, it should auto box any int value to generate an integer, which will then match unconditionally against that. But it will compile, and it gives you all the values you can possibly pass to it, even the ones that fit into byte, will result in integer. So byte is unreachable. Therefore, there is pattern dominance. Again, I believe this to be a bug, and Gavin agrees with me. So there is a situation where they will probably change this in the future. Hence why this is still a preview feature. Right, how am I doing for time? Not so well. Guarded patterns. Okay, this is where life also gets interesting. Okay, what we can do now is we can do something like this. So we're still using our primitive int, and then we're going to use a switch expression, and that needs to be exhaustive, remember. So we will have three cases. We'll have a case for 0, which will return 0. We'll have a case int I, when I is less than 0, returns negative. Case int I, when I is greater than 0, returns positive. So the idea of a guard is that you use this thing, that when, so you're matching against a pattern for the type, int I, and then you also have when, and you have a predicate after that, which you're testing something to do with the value that you've got. So as we can see here, we've got case 0, we've got negative, and we've got positive. So who thinks this will compile? Who thinks it won't compile? Ah, okay. So the answer is it won't compile. And you look at that and you go, well, hang on. You're telling me it's does not cover all possible input values. Do we have to deal with imaginary numbers? Int can either be negative, it can be 0, or it can be positive. So why is the compiler complaining about it not covering all possible input values? And the answer is that when we use a guard, the compiler does not evaluate the guard to determine if it's exhaustive. What the compiler is looking at there is it's saying, okay, you've got a case for a constant, 0, fine, and you've got a case for int I as a pattern, but you've also got a guard against that, and the other one you've got has a guard as well. Don't care what that guard means, don't care what that guard actually does, you haven't got an unguarded pattern. So from the compiler's perspective, there might be some way of getting through there and not having all values collected. Right, okay, so now let's do the same sort of thing, but we'll mix primitives and references. Like I said, don't do this at home, don't use this in your code. So we'll have case integer reference type, I, and we'll have a guard to say if I is greater than 0, we'll print out positive. Then we'll have default as negative, and then we'll have case 0 after the default and return 0. If I pass 42 to that, who thinks we will get positive? Who thinks we'll get negative? Who thinks we'll get 0? And there's lots of people who don't know what we're going to get. Okay, we will get positive. So what's happening here is we're passing in 42. 42 is a primitive. We've got a wrapper class there, so we'll box it in. Yeah, we'll box it into a value which is an integer. Then we'll test the value, having unboxed it again, to say, okay, you've got I is greater than 0, therefore it is positive. So that will work quite happily. What about if I pass in -1? So who thinks we will get positive? Who thinks we'll get negative? Okay, anybody think we'll get 0? Okay, we do get negative because when we pass that in as an int, it will box it into an integer, I, and then it will do the test and say I greater than 0. No, it's not greater than 0, so it fails to match against that case. Then it'll use case 0, and it'll say, no, it doesn't match against 0, so we'll go to the default, and the default then prints out negative. Interesting thing about switch, which I didn't know before I put this together, is it doesn't matter in switch, doesn't matter in certain situations where you put the default. So the default can go in the middle, it can go at the top, and in a case like this, it will only be evaluated if none of the other cases match. So it'll look at all the cases first, and then it will go to default if none of those cases match. So the fact that we put case 0 afterwards, as we'll see, if we do positive or negative on 0, obviously the result there is going to be 0, because we've got a value there, 0 doesn't, the guard doesn't match, and because we match against the constant 0, we do that first, therefore it matches, and we don't go to the default, so we get 0. Right, yeah. So now, let's make it even more interesting. So we'll have case integer I when I greater than 0, positive. We'll have default negative, and then we'll have case integer I when I equals 0, 0. So if we do positive or negative on 0, who thinks we get 0? Who thinks we get negative? Who thinks we get positive? Okay, it won't compile. Now, in this case, the compiler says this case label is dominated by a preceding case label. And you go, and again, IntelliJ actually gives you a bit more information. It says label is dominated by a preceding case label default. And you go, well, hang on, I just told you that it doesn't matter where you put the default. So now you're telling me it does matter where I put the default. And that is actually true because what we're dealing with here is patterns. So if you have patterns involved, Java evaluates cases strictly from top to bottom. Again, this is another one of those sort of like slight edge cases in the way that they've done things. If you're dealing with constants, all the cases get evaluated before you go to the default. So the default doesn't matter where you put it. But if you've got patterns involved, then it does matter where you put the default, because if you put it before a pattern, then you get pattern dominance. Okay, let's change that slightly. So the guard is now case integer I when I equals 0. We'll print out 0 in capitals, and case 0 as a constant, let's print out 0. So first thing is, who thinks this will compile? Okay, right, well, assuming it compiles, who thinks we get capital Z 0? Who thinks we get lowercase 0? Okay, the answer is we get uppercase 0. It does compile, and we get uppercase 0. And yeah, guarded pattern labels don't dominate constant labels. So the fact that we've got case integer when I equals 0, remember the compiler doesn't evaluate the guard to establish pattern dominance. So it will say, okay, well, you've got a case integer I when something, but I don't know what that something is, I don't consider it, and I've got a case 0 there. So it will compile, but when you run it, obviously you've got auto boxing happening, which turns it into an integer I, then it matches against that pattern, then it looks at the value of I and says, is it 0? Yes, it is. So it will print out capital zeros, 0 in capitals. Yeah. So now, if we unguard the case integer I, and so we've still got case integer I, we've got default, we've got case 0, and we do 0. So who thinks we get positive? Okay, who thinks we get negative? And who thinks we get 0? Okay, we get it won't compile. So again, what we've got is this case label is dominated by a preceding case label. But it's like, hang on, you just told me that the constants, so hang on, what was the last one I said? Yeah, guarded pattern labels don't dominate constant labels. But that's the key there. Guarded pattern labels don't dominate constant labels, but pattern cases do. So it won't compile because you haven't got a guard there, and so it will say integer I will match against 0. So it doesn't have to worry about the guard, it will just say, well, integer I will match 0, so that's going to dominate the case for 0 as a constant. So there you go. So that's just to summarize what we've been through there, that journey that we went through. Modern Java features are very powerful. I mean, pattern matching is a great addition to the programming language. Switch expressions are very useful. That's all good stuff. And they do reduce the amount of boilerplate code that we have, especially if you look at the way that switch expressions work with the arrow operator and not having to have separate cases for everything, comma separated list and so on. Sometimes things don't behave quite as you expect them to, and I think I've demonstrated that pretty well with the examples I've given you. Almost always, this is logical and well thought out. There are a few situations, as we saw, or two situations where things are a little bit different and they're still working on some of that fine-tuning to make sure that they've got every situation nailed down and it does work the way that it should work. Yeah, preview features, and like I said, the IDE is very good. It will help you to understand what you're doing and where you might be doing things wrong. So that is the end of the session on Java puzzles. So thank you very much. Question?
So is there any discussions about moving away from patterns from, you have 3 different switch. So is there any discussions about duplicating, just going into more readable code and less SK?
I haven't heard of any. I think it would be too complicated to try and, I get what you're saying, to try and deprecate the way that the switch expression, the switch statement works, and try and move it that way gradually. I think because switch is so fundamental to the language that it would just break too much code if they tried to move it in that direction. So they've tried to take the best path that they could by making switch expressions exhaustive, and then anything which uses newer features and so is an enhanced switch statement, also making that exhaustive as well. But I just don't think they're ever going to get to be able to make switch statements exhaustive. Yeah.
What is the practical use case of using primary types and in switch?
Oh, there are lots of good examples. I mean, I can't really think of one right off the top of my head, but if you're dealing with numerical values, and you want to have, essentially, it's, a switch statement or a switch expression is a replacement for if then else. And if you've got a complicated thing like that you need to deal with numeric values, then being able to do that through using the switch does make a lot of sense. So I can see that there are situations where it would be useful. Yeah.
But if you're using the value, so we already know how the value will switch, like in which case the value will fit. So we'll put the cases according to that. So the permitted types is not making.
I would suggest reading the JEP that explains that particular feature, because it does a better job of explaining it than I would. And they've got quite a few examples in there. So I would look at the JEP for that as a good way of understanding the theory behind why they introduced it. Yeah.
I'll just say that as an old programmer, I worked with Visual Basic. And one of the things Visual Basic did in their switch is you could do ranges of value. And in leaving VB, going to C, C++, and then Java, I kept begging for that. So guarded patterns, I use them. Everyone is int I. It's the when that gives it the power. And you could put an and in there and create complex statements that you have to do if, else, if in a switch. And that's what excites me about that.
Yeah. Okay, so second session is about keeping your Java hot by solving the JVM warm-up problem. So first question here is, so who has heard of Azul? Okay, most people, good, okay. So obviously Azul is a company that does Java, and we do JVMs, and I'll talk a little bit about some of the things we do as we go through, but this is not a sales pitch, don't worry. This is technical, but I will talk about some of the stuff we do with what we do in terms of JVM improvements. Right, so when we talk about warm-up, we need to understand what's actually happening when you start a Java application. And there's three parts to this. The first is the JVM itself starts up. The JVM is an application, it's written in C++, it's compiled into native instructions, and it runs just as any other application does. So when you start it, it has to be loaded, and it has to start up itself. So you load and initialize the JVM. But there's also one other thing that happens at the point where the JVM starts up, which is kind of interesting, which is every single time you start up the JVM, for all of the bytecodes you have in the instruction set, it will create a template for each instruction, which is the native instructions that it maps to. The reason it does that is because when you run on a machine, yes, it might be an Intel machine, but there are obviously different types of Intel processor, and there's different versions of Intel processors where you've got certain instructions available on some microarchitectures and some instructions are not available. Good example is AVX, so vector operations. Intel has AVX, it has AVX2, and it has AVX 512. So what the JVM will do is it will figure out what are the best instructions to use on the platform is actually running on to do the bytecodes in the instruction set. Doesn't really make that much difference in terms of performance, but it's just designed to give you that just a little bit of an edge.
So imagine that they created a JVM not only per architecture, but like per architecture plus additional set of instruction. You could imagine that you wouldn't need those templates, right? I mean,
absolutely, yes. And in fact, what you're almost describing is Project Babylon.
Project what?
Babylon.
Babylon?
Yes. So Project Babylon is looking at how the JVM can use things other than the CPU. So you can actually use GPU as well. Yeah. And so it's sort of somewhat like what you just described, but yes. There is some work going on in that sort of direction. Once we've got the JVM started, we need to start our own application. And that will be in the form of a jar file maybe, you've got a set of class files, and you need to load some of those classes to make your application work. Obviously you need the one that's got your main in it, assuming that you're using main. You load those classes, you have to do the initialization for the classes, verification, static initialization, all that sort of work. And then there'll also be application-specific startup. You get to your main, you need to create a connection to a database, you need to set up a socket to listen on your server or whatever, and that's all the application-specific initialization. Then you've got application warm-up. An application warm-up is where the application is now running, but it's all bytecodes. And bytecodes need to be compiled into native instructions to make them run faster. And we do that on a method basis, so I'll talk about that in a moment. That takes time, and if we look at the time it takes, or how quickly we can do each of those phases, JVM startup, very quick. There's nothing really we can do to improve that. It's, it's an application, it starts up, it gets going. Application startup is quick, depending on how many classes you need to load. If you've got thousands of classes, that will take more time, but mostly that's pretty quick. Application warm-up can take a long time. In terms of compilation, just-in-time compilation, you can be talking about minutes, you could be talking about hours in terms of, I don't know, have you got any examples of longer than hours for warm-up?
We have a couple, especially when you're using Spring Boot.
Yep.
And then any of those big applications are
Yeah. Yeah.
So when you're talking about, I mean, such long warm-up time, you mean that you're waiting for the JVM to be like as hot as possible, like it has predetermined all the different paths?
My next slide. Yes. So essentially, if you look at the typical performance graph for a JVM application, this is the performance being delivered by the JVM. So it's not the throughput of your application where you're doing specific things. But if we look at how much performance the JVM is delivering to your application, it tends to look like this. So on the left-hand side, you've got very slow when you first start up, and the orange bit there is where we're doing just interpreted bytecodes. So every bytecode gets interpreted and gets converted to this template. When we see that methods are being run frequently, we count how many times they're being called, we hit a threshold and we say, right, let's compile that into a set of instructions for the whole method. And we'll use the very imaginatively named C1 JIT compiler to compile that code quickly and get it running as a set of native instructions. So that gives us a bit of improvement in performance. That's the green bit. What we also do at that point is we profile how that method is being used. So we inject some code to see what's happening as the method is being used. When we get to another threshold, so it's being used a lot, then we use the equally imaginatively named C2 JIT compiler to recompile that code using the profiling information that we have. And that will apply a lot more optimizations to the code to give you better performance. So C1 is all about compiling code quickly, C2 is about compiling code to run quickly. And that's where we see the blue there. And over time, more and more methods will be compiled by C2 until you get to this steady state here where all the frequently used methods have been compiled with C1, compiled with C2. The other thing you see here are some dips in performance, and those are due to what are called de-optimizations. And I'll explain more about what a de-optimization is in a moment. But essentially, to answer your question, that time that we take to get there, that's the warm-up time. How long does it take to compile all the methods that we use frequently? And as Jay was saying, with things like Spring Boot, because there's so many classes involved and multiple paths through the code, it can take quite a long time to identify all the methods that we do need to compile.
Unless you do the AOT compilation.
You're just stealing my thunder. You're stealing my thunder. You need to wait 2 slides. Okay. So, yep. Question?
Sorry, this is a question of what are the 2 axes?
Oh, the 2 axes. So, x-axis is time, and the y-axis is speed. So basically, the speed that is delivered by the JVM. 100% here, 1 is basically the maximum that you get for that run of that application. It's not really a number that it's just saying that's the maximum you get when you run the application and it's fully warmed up. Yeah. So the other problem we face is that there's no memory associated with running your JVM. So you run the JVM, it goes through this process of identifying methods, compiling them, recompiling them, profiling, and so on. When you start the application again, it does exactly the same thing. It's got no memory of what it did before, And you can start it as many times as you like, and it has to do all of that work every single time. What we'd really like to do is...
There's also, if you've got multiple instances.
Yes.
Clustering and stuff like that.
Precisely, yeah. So when you start things up, it just starts from cold and has to warm up. What we'd really like to do is run and get it warmed up and then continue with the same level of performance. So we have 100% of our performance right from the very beginning, and every time we start up something, we can do that. So what I'm going to do now is explore different solutions to this problem. Okay, so the first one, which was already hinted at, is what about ahead of time compilation? So when I started working with Java back in the mid-1990s, Java was very slow compared to natively compiled C and C++, because we hadn't got to the stage of having JIT compilation at that point. And I know that a lot of people said, well, Java's very slow, so why don't we just compile it in the same way we do C and C++ into native instructions and just run it like that? And that is definitely a solution, which is ahead of time compilation. So let's look about that. So if we compile Java source code to native code, which is the traditional approach, ahead of time static compilation. We don't have to interpret any bytecodes, so that's good. So we don't have slow running code at the beginning. We don't have to analyze where the methods are being called frequently, so that's good. We don't have to do that work. We don't have to compile the code as the application is running. And that's another problem, if you like, with the JVM, is that not only are you having to figure out which methods to compile, you're compiling them at the same time the application is trying to do work. If you're in a resource-constrained environment like a container that's got 2 vCores, if one vCore is doing compilation and only one vCore is able to run application code, you've immediately got a 50% drop in throughput as you're doing your compilation. So that's a downside. And if you do ahead of time compilation, you don't have that problem. And of course, because it's already compiled, you start immediately at full speed. Now, this is the approach that Graal Native Image has taken. Who's heard of Graal Native Image? Yeah, pretty much everybody, yes. So Graal Native Image has been around for a while, and it was a project started way back in the days of Sun. It started out as the Graal JIT compiler. There was the Truffle language framework. There's the Substrate VM, and a few other bits and pieces. And when Oracle took over, they kind of brought some of this together and they created this thing called Graal Native Image. Essentially doing ahead of time compilation, taking an application, compiling it and running it, and great. However, the Graal team have never got on well with the Java engineering team at Oracle. And so they finally settled their divorce recently, and now they're very much two separate teams within the organization. There have been some announcements about the sort of separation. There's no longer going to be the Graal JIT compiler included in the OpenJDK. They've removed, or they're deprecating the compiler interface. So essentially this could have been the answer to all our problems, because of course, if we think about it, I've just said, don't have to do bytecodes, don't have to do warm up, all of that just disappears. That would be wonderful. However, not so fast. What I mean by this is that ahead of time compilation is by definition static, as in it doesn't change. And the problem is that you're compiling your code before the application runs, meaning you don't know what the application is actually going to do when it's running. Now, because it has no idea of what the code is going to do when it's running, it can only apply certain optimizations. It can do things like loop unrolling, it can do things like hoisting variables, it can do things like dead code elimination. But there are a lot more sophisticated techniques that can't be used if you don't have a view of what the application is doing at runtime. There's a thing called profile-guided optimization. It's been around really since the beginning of compilers, which tries to address some of that problem. Essentially, you say, right, compile my code statically without any idea of what it'll do, run the application, track what it's doing, build a profile of its run, and then recompile it statically, but use that profile to figure out some more optimizations that you can do based on what it was doing. But it is still static. It doesn't change as the application runs. So the other thing that's very important about using JIT compilation is the idea of speculative optimizations. This is where you actually see places you can get much better performance even than statically compiled code. I'll give you a couple examples of that. First one is what we call inlining monomorphic sites. If I have a class called animal, and I've got in there a state which is color, and I mark that as private because I'm a good object-oriented programmer. In order to access the color instance field, I need an accessor method. So I'll call it getColor. All it does is return color. If I use that in my application, I have to reference the method and I call getColor and I get my color. Problem with that is it's very inefficient from the compiled code point of view, because to call a method, the compiler has to push a stack frame on, it then has to execute the method's code, which is just returning the color, and then it pops off the stack frame. So every time you're doing that, you're creating a stack frame and popping it off. Not good. So the compiler will optimize that by saying, okay, even though you've marked that field as private, I can still compile that code and respect what you've done, so I'm not breaking the contract, and just treat that as if it's private. So every time you want to call the color, it compiles as if it's a public field, and therefore we don't need the stack frame and we get the value quickly. That works so long as we don't do any dynamic class loading. If we do dynamic class loading and we introduce a new animal that's, say, a chameleon, where the color could change and we need to calculate what that color is, then we can't just use animal.color. We have to call the method directly and do the work. So compiling it statically, where we have animal.color, isn't going to work. So we can't use that optimization in that case. A slightly more complicated example is around what we call branch analysis. If I've got a method like this, which computes a magnitude based on a value, I've got an if statement here. So I'm doing a test to see if value is greater than 9. If it is, I'm going to call another method called compute bias with the value. And if it's not greater than 9, I simply set bias to be 1. And then I'm going to return the log base 10 of bias plus 99. Branch analysis says that when we profile that method as it's running, we count how many times it goes through the true branch and how many times it goes through the false branch. When we come to JIT compile this code, we can look at those numbers and we can say, actually, we have never been through the true branch. So there's a 0 count on the true branch. Let's assume and speculate that that is going to continue in the future. And we're never going to go through the false branch. There's some weird situation, sorry, we're never going to go through the true branch. That would be some weird situation that just doesn't happen. So we can recompile that code based on changing it quite significantly to get better performance. What we can end up doing is saying this. So we still need to have an if statement to say if the value is greater than 9, because that was in the original code, so we've got to have that. But rather than actually doing something that's specific to the application, we will call this thing called uncommon trap. An uncommon trap is where we de-optimize. We've compiled this code based on a speculative optimization. That now is false, so we have to throw away the code because it's not going to work. So we throw away the compiled code, we go back to using the bytecodes, maybe going back to use C1 compiled code, but we can't continue to use this code as it's being compiled. But if we do continue to not have a value greater than 9, we can simplify our return statement because we know that we're always going to set bias to be 1. 1 plus 99 is 100. Log base 10 of 100 is 2. So let's just return 2 rather than do all that extra work. So this is the kind of thing that gives us a lot better performance by doing JIT compilation, because we're seeing what's actually happening in the application as it runs. And if we go back to the graph I showed you earlier, if this is our JIT compiled code and this is our 100% level that we get when we've compiled everything, those dips, as I said, are the de-optimizations where those speculative ideas proved to be wrong. We had to throw away code. If we compare that to ahead of time compiled code, we would see something like this. Yes, we get 100% of the performance immediately, but the issue is that the performance we're going to get is not going to be at the level that you get with JIT compiled code because of those speculative optimizations. or measurements that we've done at Azul, we estimate that at least 50% of the improvements in performance we get are down to speculative optimizations. Even if we use profile-guided optimization, we recompile based on some profiling of the application, we're still not going to get to that 100% level that we get with JIT compilation. So this is the sort of situation where having JIT compilation can deliver better performance than natively compiled code. So even C and C++, we can sometimes outperform them by doing JIT compilation.
Do you agree with some people? Yeah, also. So you're going to talk about it, but in case you don't mention that, can you like sum up, because I've seen some people in conferences like summing up things like, oh, if you need like, for example, something that needs to start super fast without a lot of work, like for example a lambda or whatever, yeah, sure, exactly.
Yeah, yes. Yeah, basically, when to use AOT. There are some very good situations when using AOT makes sense. And that is where you're basically doing short-lived microservices. So AWS Lambdas is a great example because they're short-lived and you don't really care about waiting for the application to warm up. You just want to get that function done, return the value, whatever, do it quickly. Similarly, you're not going to be doing a lot of garbage collection because it's a function that doesn't tend to generate a lot of garbage. So yes, for short-lived things like that, AOT, Graal native image would be a good approach because it solves the problem and it gets you, also tends to be a smaller footprint in terms of the overall space that's required for the application. So yeah.
It's just something that that makes me feel weird when you talk about AOT is because I've been following a lot what the Spring team are doing, and they have really focused on. I mean, for Spring performance, somebody like Sebastian Deleuze, he has focused a lot on AOT and trying to make the most of Spring and Spring. The most common third-party dependencies to be very well behaved with AOT compilation, and that's what they did. The thing is that they are promoting AOT compilation not only for native, but also as a way to, I mean, as an additional step before like packing up everything inside your jar. So, do you think that this? All right. So, of course, you talked about AOT in the context of native, but do you also share this point of view that in the context of AOT for a jar-based deployment, is it still worth it according to you, or is it something that will always be beaten in the long term by JIT instead?
Yeah, I mean, again, for things like Spring, as you say, they've done a lot of work on that side of things. And what you tend to see, in my opinion, is that you start going down a particular route in terms of how you write your code to fit that model. So a good example, a different example is where you're trying to tune garbage collection. So you end up writing a framework which doesn't generate any objects. So you go for a garbage-free type of approach. So which is very difficult to do. Whereas if you just let the garbage collector do its work, you avoid all of those issues. So yes, Spring is certainly like looking at that as a way of improving performance. But I think the problem is for the framework, that's great. But if you're then writing code on top of that, you need to be aware that that code is more general and so needs things like this. Are you gonna?
I was weirded out by AOT at Java. Just write once, run anywhere.
Yeah, well, yes, it does break the right ones to run anywhere. Yes, completely.
So it's just,
Yeah.
That's just for the
Yeah.
performance, we just decided
Yeah.
to go that route.
Yeah. Okay. Right. Solution number 2. What about if we store the JIT compilation data? So this is what we've done at Azul, is we've developed this, so we have our own JVM called Prime, and part of that is what's called Ready Now. And the way that works is to say, okay, let's run the application. So we compile it as normal bytecodes, we run it through the JVM, we let it warm up. Once it's warmed up, we take a profile of that running application. So this is similar to the idea of profile-guided optimization, but what we're actually doing is profile of JIT-compiled code. And the profile that we record contains 4 things. It's got all the currently loaded classes whenever you take that profile. It's got all the currently initialized classes, because that actually could be a subset, because when you load a class, you don't have to initialize it immediately. All the profiling data that we've collected up to that point, so all the methods that are being compiled, what profiling information we use to optimize those, and then de-optimizations that occurred when we were running, because obviously we don't want to make the same mistake a second time. What we can do with that is then restart the application, and we can put on the command line, here's the profile that we want to use for that application. When we do that, the JVM can immediately say, right, I know all the classes that I need to load straight away. So it can load those classes, also knows which classes to initialize, so it initializes all of those, and then it knows all the methods that it needs to compile straight away, compiles those methods using the profiling data and avoiding the de-optimization, so it knows which speculative optimizations to avoid. So that we do all of that before you get to your main method. And that means that when you start running your main method, you're running at about 97% of the performance that you had when you took that profile. Can't quite get to 100%. There's certain things that the JVM spec makes us do that means we can't get to that 100%. There's things like lambdas, for example, and the invoke dynamic bytecode that prevent us from doing that. But 97%, after about 5 transactions, 10 transactions, you'll be at your 100% of your performance that you had before. So if we look at a simplified version of the graph that I showed you earlier, where we've got the warm-up slope and then we get to our steady state of optimized code, without Ready Now, that's the shape we get. If I show you the same shape with Ready Now, we get something that looks a lot more like the one that we have with AOT. Yes, it's still got a slope to it, but that slope is much steeper, and we get to that optimized level of performance much more quickly. So this is really good. You know, it gives us a better profile in terms of how much performance we can get out of the JVM. Of course, the observant amongst you might notice that there's a little bit of a gap there, which is where we don't do any application work at all. So you get 0 performance, and then you get a lot of performance. But there's a period where you're getting 0 performance. And that's obviously where we have to do all that work. The work has to go somewhere. So we have to load all those classes, initialize all those classes, and then compile all the methods and do all that work. But once we get past that point, everything is good, and we get a steep graph and so on. So the places where this makes a lot of sense is where you've got things like trading systems. Trading systems, you have a very predictable thing where you know that the bell is going to ring at 9 o'clock in the morning, and that's when you want your application to be running at full speed. Because it's predictable, you simply say, right, I know there's going to be this dead zone where I'm not doing any application work. Let's do that, start the application at 8:45, does all the work, and then at 9 o'clock it's ready to go, and off you go with the performance you need. So again, thinking about where this makes sense is where you've got that predictability. Microservices, unless it's a longer running microservice, this may not be the ideal thing, but if you have got a longer running microservice and you're not too worried about how long it takes to get past that initial dead spot, then it can be useful, but it depends on the profile of your application. Now, related to that is Project Leiden, which is another project under the OpenJDK. And what that's goal is all about improving startup and warm-up time, which is good because that's exactly what we're talking about here. Now, this project's been around for quite a long time. It's actually it was started probably about 3.5 years ago. And for a good 2 years, they did absolutely nothing. I mean, they didn't even have a mailing list for the first 2 years. And everybody thought, oh yeah, they've kind of started this project. Somebody had an idea about it, and then nothing happened. But the reality is they have started doing some work on this now, and they've delivered a number of pieces, and they're looking at some more. So there's 3 specific parts to this at the moment. First of them is what's called AOT class loading and linking, which is JET 483, and that was delivered in JDK 24. Essentially what that does is looking at this idea of making sure all the classes you need loaded are loaded quickly and initialized. It's built on some slightly older technology that was called application class data sharing that used to be a commercial feature in the Oracle JDK. And what that does is it says, okay, when you start your application and you run it, you obviously load a number of classes and you initialize a number of classes. What that does is verification of the classes, and then it builds data structures internally for the JVM to use. So when you take a snapshot of your classes, essentially what it does is it writes out those data structures to a file in the file system. When you start it again, rather than having to go through the process of verifying the classes and loading the classes, initializing the classes, it simply says take that file, map it into memory, and point the data structures at where that is, so it's all ready to go. So it improves the performance of startup. It's not something that makes a huge difference. It will reduce startup a bit, but it's not going to have a really significant impact on a startup improvement. The other bits they've done is around AOT method profiling, and that's essentially what I said, where you take the profiling data that's been collected as methods are compiled with the JIT and store that in an external file so that you can reuse it later on. Similarly, they've got AOT ahead of time object caching with any garbage collector. They had a problem where they were doing the object caching with ZGC. I think, do you say ZGC or ZGC here? I can never, ZGC, because as an Englishman it's ZGC. As an American it would be ZGC. So yeah, ZGC was causing them some problems, so they've solved that issue. And then there's a third part to it, which is AOT code compilation. That's still a draft JEP at the moment, hasn't been included yet. And that's the idea of taking that compiled code from a training run and reusing it when you restart the application. So a lot of this should sound very familiar because it's essentially everything that we did with Ready Now. Oracle looked at that and said, this is really good stuff. We're going to ignore it completely and develop it ourselves because not invented here for Oracle. Solution 3, what about if we decouple the JIT compiler? Now, if we look at the JVM architecture, which is probably difficult to see with the horrible colors and text that I've used there, but essentially top there you've got the class loader, which does all class loading verification and so on. You've got the runtime data area, which is your heap and your stack and so on. And then the important thing is the execution engine at the bottom. That's the interpreter, the JIT compilers, and the garbage collector. And we looked at that and we said, how can we improve the performance of the JVM further? And we said, JIT compilation. JIT compilation is the thing that really means that we have a long time for warm-up, we have to compete for resources and so on. And the other thing we did was we said, okay, for speculatively optimized code, we need to consider code as a unit. By that I mean that you're going to have a method that gets compiled by the JIT. And that method is compiled based on these speculative optimizations. So there's a set of assumptions that are used to compile that code. Going back to the examples I showed earlier, you can say, okay, I've got a method here, part of my class, which is compiled based on only one getColor and only values greater than 9 or greater, that match against that. So those speculative optimizations we saw before, those are used to compile that method. So you could have the same method compiled different ways using different speculative optimizations. So we need to treat each one as a unit and a set of assumptions that we have that hold true. Now the next thing that we need to think about with the JIT is that JIT compilation has cost. If we want to improve the speed of our application by getting more heavy optimizations takes time, like real time. And essentially what we end up doing is making a sort of compromise in terms of that secondary JIT compilation, so the C2 compiled code. Even though it's more heavily optimized, we still have to make compromises thinking about how long is it going to take to generate the code compared to the level of optimization that we can get from that. If we've got lots of resources, if we've got a 64 vCore machine with 64 gigs of memory, fine, we can throw lots of resources at doing the compilation, that's okay. But if you're running in a 2 vCore container, you've only got 2 gigs of RAM, that then starts to become more of an issue. As I said, you can reduce your throughput by 50% just by doing 1 vCore running compilation. Similarly, if you have very memory intensive compilation, you can end up getting out of memory errors, even though you haven't actually really run out of heap space. You've just run out of actual physical memory associated with the container. So we end up with a compromise. And what we said was, okay, well, let's look at an example here where we've got a 2 vCore container and it's running an application using OpenJDK. So the hotspot VM, and this is what we see in terms of performance. So the top line is showing throughput over time. And we can see we've got a nice steep graph there which starts up and we hit our optimized code pretty quickly. So that's good. We want that. That's wonderful. And then if we look at the bottom line, which is showing CPU utilization, we can see there's a bit of a spike at the beginning where we're thrashing the processors, and then once we've done our compilation, it drops down and we run at a fairly steady state after that. What I can then do is overlay on top of that the same application running on the same machine, but this time using our JIT compiler, because Azul has a different C2 JIT compiler, it's called Falcon, based on another open source project called LLVM. And what that looks like is this, so the blue line. Now, if I look at the right-hand side of the graph, I go, yes, this is really good, because I've got roughly 15% more throughput. That's wonderful. So I'm getting faster code for my application. But unfortunately, if I look at the left-hand side, I run into this problem of it takes longer to warm up. So we're going through a much shallower graph, and we're seeing lots of dips in performance because we're much more aggressive in terms of our speculative optimizations. We try all sorts of different tricks to try and get better performance out of it, and a lot of the time those don't work out, so we have to throw away code and recompile it. And if we look at the CPU utilization, that also matches what we're seeing on the top, where we're seeing a lot longer, where we're actually using all the resources we've got and competing against the application. So we said, right, to solve this, what about if we decouple the JIT compiler from the JVM? Let's take it out and put it into a centralized JIT as a service. When the JVM wants to compile a method, rather than doing it locally using the vCores of that container, let's send it across the network to our cloud native compiler, have the cloud native compiler do the compilation. We can provision lots of resources for that, have it do the compilation, pass it back to the JVM, and the JVM then gets the code ready to run. If we go back to that graph I showed you before, now what I'll do is overlay the same application running on the same machine, but this time using the cloud native compiler. So it's not doing compilation locally, it's using the remote compiler to do the work. And we see this. And if I drop out the blue line to make it more obvious, this is much better, because now we've got almost the same slope of graph that we got with OpenJDK, very fast warm up. Takes just a little bit longer to get to that optimum level of performance, but not anywhere near as long as we saw before. And so we're getting 15% more performance very, very quickly. And on the bottom line, we can see that because we're not doing the compilation locally, there's a brief spike at the beginning where we're doing class loading and initialization, but then it drops down very quickly to about 1 vCore's worth of CPU. So in this situation, you might even be able to get away with cutting down from 2 vCores to 1 vCore and still run that service, microservice, in that container. So obviously this is really good, but people will say, well, hang on, isn't this just shifting the cost? So, yep, you've still got to provision your cloud native compiler and you're just shifting the work from one place to another, you've still got to pay for it. Well, yes, you do, but there are some big things that we can do in terms of optimizations. Because yes, we're shifting the work from one place to another, but now we've got a long running service, meaning that when we compile a method, we send it across to our cloud native compiler, compile it, pass it back. When you start up the same microservice, another instance to address load, compile the same method, pass that across to the cloud native compiler, it's already got it compiled. So it can pass it straight back without having to do any work. That's where we need that fingerprint, if you like, where you've got the method class, or the method bytecodes, and the set of assumptions that you need in terms of those speculative optimizations. So you need to match that to make sure you give the right compiled code back. but it does give us that long-running process that we can then store the information and pass it back. The other thing that we can do, which is really nice, is we can say, okay, we will compile that method at, let's say, optimization level 3, and we can get that back to the JVM that's called for it quite quickly. But if we're then sitting there and we've got some resources available in the cloud native compiler, we're not doing anything, sitting idle, let's take some of those methods and now let's recompile them at optimization level 4. That gives us a longer time to actually compile it. We've got to go through a lot more work, but eventually we'll get better optimized code for the same method. Next time that service or microservice or class needs that method, then it's got a better version that we can pass back to there. So you get even better performance with that. Now, a couple of things to say about this. One is we don't actually remove the JIT compiler from the JVM. So if we send a message across to our cloud native compiler, it times out on the network, there is still a JIT compiler, we can do the compilation locally. So that doesn't cause a problem. The other thing that a lot of people say is, well, hang on, doesn't this cause a lot of network traffic? Isn't this going to introduce like latency and stuff like that? The answer is no, it's not an issue. On gigabit speed Ethernet, the amount of data that we're transmitting across the network is very minimal. Most methods are quite small. Profiling data is quite small as well, so it's not an issue for those kinds of things. Last thing to talk about is, what about if we save the whole application state? Yep, good. That's 7 minutes. Right, so in Linux, there is a thing called coordinated resume in user space, or CRYU. Now, the idea behind this is to give you a very similar kind of approach to what you have with your laptop. Because if you think about it, you have your laptop, you open it up, you're running a web browser, you've got your IDE running, you've got a Word document, something like that. Now, you need to leave the office and go home. So what do? You close your laptop, you go home, open your laptop, all those things are there exactly as you left them. Why can't we do the same thing with an application? So that's what CRYU is about. It's about storing the state of an application in user space so that you can then reconstitute it at a later point in time from exactly the place that you left it. So when you close the lid, then you open the lid again. Essentially, this is very similar in concept to the good old days of when we had a single CPU with a single core, and we had we had time-sharing operating systems. To think about that, time-sharing operating systems. To give the illusion of running multiple processes at the same time, you simply swap between those processes very quickly. And so what you would do is you would take the program counter, you would take your stack, you take your registers, write it to memory, that swaps out the process. When you need to bring it back in again, you bring everything back from memory, start from exactly the same point. All we're doing here is the same thing, but writing it out to a set of files rather than memory, and we can persist it for longer. Now, we looked at this and we thought, this is good because the JVM is an application. Why don't we just create an image of a running JVM and then we can restart it from the same point? But the problem is, it's not quite as easy as that, because yes, that will theoretically work, but trying to do it reliably is very difficult. If you think about it, a lot of applications will have database connections, they will have network sockets, they will have open files. If you store the state with all those things open, and then you try and restart it 2 hours later or 2 days later, most of those things will have gone stale. You'll lose your network connection, you'll lose your database connection, your files will be changed. So it doesn't work in the form of just simply freezing the application and restarting it. So we came up with what we call coordinated restore at checkpoint, Java on crack. And what Java on crack does is says, okay, we want to do that, we want to freeze an application, but let's make the application aware that it's being frozen, checkpointed and restored. So your application starts running and then you decide to create a checkpoint. At that point, we tell the application that it is being checkpointed and it can do the work that it needs to do in terms of closing files, shutting down network connections, terminating database connections. At some point later, we want to restart our application And we can do that reliably because now the application is also aware that it's being restored. So where we had closed a file, network connection, or database, we can then restart those and do it in a reliable way in our own code. And then we can move on from there with our application. So we actually enforce that in terms of not allowing you to do a checkpoint if you have got any open sockets or files. How this works is very simple. We have a little API that has an interface called a resource. That resource has two methods that you have to implement: before checkpoint, after restore, which I'm sure you can guess where those methods get called. The idea is that the before method gets called, you shut down the database connection, you close any files. When it gets restored, you write the code to open those files, restart the database connections. And you can even do things like, if you close a file, you can do a checksum of the file, and then when you restart the application, you can do another checksum, see if they've changed, maybe reload the file, reread the file, or whatever. That works with what's called the context, because you need to tell the JVM that these classes which implement this resource interface need to have those methods called when you do a checkpoint and a restore. So you register them with the context. The context comes from the global context, which comes from the core class. So it's as simple as that. You just implement those two methods with the interface. Yeah, I need to, yes, I'm almost finished. Yeah. Now, the other thing about this is that the order that you register them in is important. So you can decide what order you want to register them in, and that's the order that the before checkpoint will be called. When we restore, the order is reversed. So it makes sense that you now have control and then you come back again. Does it work? Well, we did a proof of concept. Initially, we did JDK 17. We've also done JDK 21, JDK 25. We took things like Spring Boot, Micronaut and Quarkus and took some sample applications, and this is the results. So Spring Boot with, I think it's the pet store application, that took basically 4 seconds from cold start to first transaction. We took a checkpoint of that, did a restore, and it was doing first transaction 38 milliseconds. So that's 2 orders of magnitude faster. So we think about AOT as being a great way to get fast startup. This is a great way of getting even faster startup, and you get all the benefits of the fact you've got all your data, you've got all your application state and everything, so you're just running from the point where you started. Similar thing with Micronaut and Quarkus, about a second each, reduced to tens of milliseconds. So similarly, sort of 2 orders of magnitude. Last thing to mention is the idea of crack without cryo, and this is what we've been working on recently, because ideally we'd like to make this work on multiple platforms and not relying on cryo. So as a person who used to work on operating systems, this is a very scary concept that we came up with. And when the engineers explained it to me, I went, ooh, that sounds really dangerous. Essentially what we do is we say, let's force a crash dump of your JVM. Crash dump writes all the state out to a file. We will then take that crash dump and we will start it again from the point where the crash dump was taken. We have made this work. I have no idea how, but we have made it work. And so we can actually restart an application from the crash dump, and that gives us even faster startup on those types of things. You do need to be careful about, the other thing that's good about this is we don't need root privileges to do that. Anybody can crash dump their own JVM. We do need to have issues with the process ID and stuff like that, but it's an interesting way of doing things. The other thing that's really good about this is that when we start the application again, because we've basically got a crash dump, which is all of memory, we don't need to load everything into memory to get the application started again. We can basically just do page faults on the crash dump, and then as we need pages of memory, they get loaded in, and that gives us, again, a way of doing a much faster startup. So all sorts of things that are good there. Just to summarize, basically solving the JVM all-right problem, there is no one solution that fits everything. AOT is good for fast startup, small footprint, short-lived processes. Ready Now works well for JIT compilation data, but because of the dead spot or dead zone, it means you have to wait a little bit of time before you get the level of performance. Cloud Native Compiler is very good because it offloads the JIT workload, so you can do that in a cloud environment, things like that. Crack is very good for starting your application from a known point. And Project Leiden, as I say, is looking at a lot of these approaches and other things as well. So that is it. Thank you very much.
I have a question for you.
Okay.
When you say that if a developer is using Crack, it's up to them to actually get the context and then call, listen to the context and then react on the context, can't you imagine like an agent that would actually be smart enough to do that on behalf? I mean, that would analyze the application code and say, oh, he's loading a file here and here he's opening a socket, and then do this work for you?
Yes. Theoretically, yes, you could do that for certain situations, and like you said, with things like a open file, open socket, you could have an agent which does that work for you. But there's a lot more subtlety and nuances you need to worry about. So, to give you an example, is that we had, when we did one demonstration of this, we had a situation where we got like a cache involved, and every time we restarted the application from the checkpoint, or we did a restore, it reloaded the whole cache, and we were like, why is it reloading the whole cache? And it was because the system clock had changed between the 2 points, and so the cache was being invalidated because of the clock change. So we fixed that by adding a thing where we recorded the clock time when we did the checkpoint, and then we compared and we took the new clock time, did a delta on it, and then decided whether, based on the difference, whether it needed to invalidate the cache. So there's things like that which are more complicated that you still need to deal with in the restore or the resource implementation.
Yeah. Okay. Thank you.
So yeah.
Question as well. Would that be a good idea to prepare a container image, like just with the application ready to be restored?
Yes, and that is a great example of where this works really well, because what you do is you run the application, you create a checkpoint, and then you can put the image of that checkpoint into a container. And because it's in a container and it's isolated, you can start it up multiple times because it's within the container. The problem is if you try and start up the same application from a checkpoint on a machine more than once, it won't work because you run into the problems of the process ID. But if you put it in a container, that works really well. So yes, we've got customers who are doing that, who are actually using it in a container to get very fast startup.
Okay, if there are no more questions, we're going to move on to the quiz. So